Atoms are the building blocks of matter and have internal structure. So atoms consist of a nucleus, and a nucleus is positively charged and surrounded by one or more negatively charged electrons. So the nucleus is made up of protons, which are positively charged particles, and neutrons, which are neutral and have no charge. So the number of neutrons and protons in an atom can be represented using nuclear notation. So we have the element that we're referring to, a mass number A, and an atomic number Z. And you'll have the charge depending on whether we're looking at an ion. So the mass number is equal to the number of protons plus the number of neutrons. So if you look at the periodic table, the different elements are ordered by the atomic number. So for example, lithium has an atomic number Z of 3 and an average mass of around 7. And lithium exists with a different number of neutrons, and these are called isotopes of lithium. So for example, one of the isotopes has a mass number of 6, and the other isotope has a mass number of 7. So these isotopes have the same number of protons according to the atomic number, and therefore we can work out the number of neutrons for each isotope by subtracting the atomic number from the mass number. So this isotope of lithium has 3 neutrons, and this isotope of lithium has 7 minus 3, which is 4 neutrons. So isotopes of the same element have a different number of neutrons, but the same number of protons. Now an ion is an atom with a non-zero net electric charge. So for example, if we subject a lithium atom to electromagnetic radiation, then the electron absorbs a photon. So if this energy is equal to the ionization energy, then this electron will be ejected from the atom. So remember, by Coulomb's law, the Coulomb force is proportional to the product of the two charges and inversely proportional to the square of the distance between them. So the valence electron, being the electron in the outermost shell, gets ejected first because it's furthest from the nucleus. So in here we're looking at lithium 6. So we have 3 protons and 3 neutrons. And when the atom is ionized, so when it loses an electron, it loses a negative charge, and it thereby now has a positive charge. So it's now a lithium ion. So each atomic element in the periodic table has a unique number of protons, as given by the atomic number, which are ordered in the periodic table, and the number and arrangements of electrons affect how atoms interact. So for example, given 2 lithium atoms and an oxygen atom, so here we see oxygen has an atomic number of 8, so it has 8 protons in a nucleus, and in this case we have 8 neutrons. So this isotope of oxygen has a mass number of 16. So if we have 2 lithium atoms, then the valence electrons in a lithium atom are attracted to the nucleus of the oxygen atom. So these will be strong electrostatic forces, and therefore these atoms bond to create an ionic compound. So in this case we have 2 lithiums and 1 oxygen, and this compound is called lithium oxide. So effectively you have 2 lithiums, each with a positive charge, and 1 oxygen that has a 2- charge, because it attracted 2 electrons, 1 from each lithium. And multiple lithium and oxygen atoms bond to form an ionic solid, because of those strong electrostatic interactions. And also note that the mass of an atom is dominated by the total number of protons and neutrons in its nucleus. So electrons have a smaller mass than nucleons, being the protons and neutrons. The Bohr model of an atom is based on classical physics. And this historical representation of the atom led to the description of the hydrogen atom in terms of discrete energy states. So in the Bohr model, we model the electrons as orbiting the nucleus at a certain velocity in circular orbits, like the planets orbit the sun. So to do that, we use the electron's charge, the mass of the electron, and the electric force between the electron and nucleus. So using Newton's second law, the Coulomb force is Coulomb's constant by the charge of the nucleus by the charge of the electron on the square of the radial distance between them. And that's equal to the mass of the electron by the centripetal acceleration, which is the square of the speed of the orbit over the radial distance to the electron. So in the hydrogen atom, there's only 1 proton in the nucleus and no neutrons. So therefore, the proton has an elementary charge E, and the charge of the electron is the negative of the elementary charge. But what we do here is take the magnitude of charge. So therefore, we have the square of the elementary charge in the numerator. And now we can cancel out one of the r's, and dividing through by the mass of the electron, we get Coulomb's constant by the elementary charge squared on the radius of the orbit by the mass of the electron is equal to the speed of the electron squared. Now the orbital angular momentum of this electron is the radius of the orbit by the linear momentum of the electron. So that will be the mass of the electron by the velocity. Now given that Bohr stated that the electron in the hydrogen atom can only exist at certain energy levels, then he quantized the angular momentum. So this is equal to some integer n by Planck's constant on 2 pi. And therefore, if we solve for the speed, we have v is equal to nh on 2 pi by the radius of the orbit by the mass of the electron. And now we can substitute for the velocity. So what you'd get is n squared h squared over 4 pi squared r squared by the mass of the electron squared. And now if you do some algebra, you can solve this for the radius of the orbit. So that will be n squared by the square of Planck's constant on 4 pi squared by the mass of the electron, by Coulomb's constant, by the square of the elementary charge. And now we can plug some numbers into this equation. So we have the mass of the electron was 9.109 by 10 to the minus 31 kilograms. So we'll use SI units here. And the elementary charge is 1.602 by 10 to the minus 19 coulombs. And let me just make a bit of space here. So we know Planck's constant is 6.626 by 10 to the minus 34 joule seconds. And Coulomb's constant is 8.988 by 10 to the 9 Newton meters squared per Coulomb squared. So if you substitute n equals 1 into this equation, you'd get the radius of the first orbit, which is the ground state, as 5.3 by 10 to the minus 11 meters, or 0.53 angstroms. So that's this orbit over here. And for n equals 2, you'd have n squared is equal to 4, and therefore R2 is 2.1 by 10 to the minus 10 meters. So that's around 2.1 angstroms. So in general, the radius of some orbit n is simply n squared by the radius of the first orbit, because we use n equals 1 to compute R1, and the rest of the constants are the same. So we just compute the radius of the first orbit, being the ground state, and the radii of the excited states are computed by choosing the appropriate number of the orbit. We derive the radius of the orbit for the hydrogen atom for the different orbits n as Rn is equal to n squared by the radius of the first orbit. And recall the magnitude of the Coulomb force for an electron in a circular orbit around the nucleus is Coulomb's constant by the square of the elementary charge on the square of the radius of the orbit. And that was equal to the mass of the electron by the centripetal acceleration. So if we multiply through by r, one of these r's cancels, and then multiplying both sides by a half, we get the kinetic energy of the electron. And therefore the total energy of the orbit is equal to the kinetic energy plus the electric potential energy. So the kinetic energy is Ke squared on 2r, and recall the electric potential energy to bring a charge from infinity to a distance r from another charge, in this case being the charge of the nucleus, is equal to minus Coulomb's constant by the product of the two charges on r. So therefore the energy of the orbit is minus Ke squared on 2r. So recall that energy is quantized in the Bohr model, and as we found, the energy of an orbit n is equal to minus Ke squared on 2Rn, and if we substitute for Rn, we get n squared by the radius of the first orbit. And if we substitute n equals 1, we get the energy of the first orbit is minus ke squared on 2r1. So recall the elementary charge for an electron was 1.602 by 10 to the minus 19 coulombs, and Coulomb's constant was 8.988 by 10 to the 9 Newton meter squared per square coulomb. And we also found the radius of the first orbit was equal to 5.293 by 10 to the minus 11 meters. So if we substitute these values into here, we get the energy of the first orbit as 2.179 by 10 to the minus 18 joules. So let me just get rid of this. So if you recall, 1 electron volt was 1.602 by 10 to the minus 19 joules. Then we can obtain E1 in electron volts, which is minus 13.6. So once we've got E1, then this expression for En is simply E1 on n squared. So now using this expression, we have E1 is minus 13.6 electron volts, and the energy of the second orbit is E1 on n squared, which is 4. So that would give minus 3.4 electron volts. And E3 is minus 1.5 electron volts, and so on. So the first orbit has the lowest energy, and the energy increases and approaches 0, where the atom gets ionized and the electron escapes from the atom. So the first ionization energy of hydrogen is well predicted by the Bohr model. So in other words, if the electron absorbs a photon with energy of 13.6 electron volts, the electron gets ejected from the atom. Now the electron has to absorb a specific amount of energy to jump from the ground state to an excited state. So to jump between these energy states, it has to absorb an amount of energy equal to E2 minus E1. So that will be minus 3.4 minus 13.6 electron volts, which is 10.2 electron volts. And to jump from the ground state to any other energy level, so in this case n equals 3, the electron has to absorb E3 minus E1. So that will be minus 1.5 minus 13.6, which is 12.1 electron volts. So when the electron's in the excited state, it always wants to jump down to the ground state. Now if the electron was in the excited state, so it's orbiting the nucleus in the second orbit, then the photon that it emits to jump back down to the first energy level has electromagnetic radiation energy of E2 minus E1. So note that the electron will always want to return to the ground state, which is its most stable orbit. Now note that if the electron was in a ground state and it was to absorb a photon with an amount of energy that's less than 10.2, for example, so it would end up here. Given that the electron can only exist in orbits that have specific energies, because energy is quantized, then in this case the photon will just pass through it. And if the electron absorbed energy greater than its ionization energy, then it gets ejected from the atom. The standing wave model of electrons accounts for the existence of specific energy states of an electron that are allowed in an atom. Because the electron's orbit circumference, which is 2 pi by the radius of the orbit, must be an integer multiple of the electron's de Broglie wavelength, which, recall, was equal to Planck's constant on the momentum of the electron. And note that the Bohr model assumes orbits are circular, but in reality the orbital shapes are different, and the Bohr model works well for the hydrogen atom because it only has one orbital. So recall our standing wave model. We had nodes where there's no motion, and after some time the wave looks something like this. So there's maximum displacement at the antinodes and zero displacement at the nodes. So if we wrap this wave in a circle, then it represents the orbit of an electron, which looks something like this. So we have this node meeting with this node when we wrap the wave in a circle. So essentially, if we look at the solid line, we have our node, and when we go to the next node, we have our peak of the wave, and from this node to the next node, we have the valley. And after some time, our standing wave looks something like this. So from this node to the next one, we have the valley, and if we continue on to the next node, we have the peak of the standing wave at this point in time. So this is for the first orbit. And for the orbit n equals 2, we have 2 waves wrapped together. So 5 nodes become 4 nodes where there's no motion. So from the first node to the next one, we have a peak, and to the next node we have a valley, and to the next node we have a peak, and to the next node we have another valley. So we can see there's maximum displacement at the antinodes, and then after some time the standing wave looks like this. So from node to node we have a valley, and then we have a peak, and then a valley, and then another peak. So given that the electron's energy is quantized, it can only exist at certain orbits. So therefore we cannot have this case, which is 1.5 wavelengths. So in other words, the electron cannot exist between these 2 orbits. And if you continue this further to n equals 3, you'll have standing waves with 3 wavelengths, 4 wavelengths, and so on, which become more complicated to visualize, but this is the general idea. The following energy levels of an atom are given, and in part A, we're asked to determine the possible photon energies that can be emitted when the atom returns to its ground state. So if we suppose an electron was here, it would have to emit a photon that is carrying energy equal to E2 minus E1, which is minus 76 minus 122 electron volts, or 46 electron volts. And if the atom was in the third energy state, then the energy that an electron has to emit is E3 minus E1. So that would be minus 5 minus negative 122, or 117 electron volts. Now in part B, if the atom is in either energy state and it is subjected to a photon carrying 20 electron volts of energy, what will occur? Well, if the atom was in the first energy state, then absorbing 20 electron volts of energy means that the electron has to exist between the orbits n equals 1 and n equals 2, which is not possible. So the atom in this case would be transparent to the photon, so the photon would just pass through it. And similarly, if the atom was in the second energy state, then if the electron absorbed 20 electron volts, then again the electron cannot exist between these two energy states. So again, the photon will pass through the atom. And if the atom was in the excited state, n equals 3, then if the electron absorbed the photon, it would get ejected from the atom. So basically the atom gets ionized.